Hi, I'm Jordan Johnson, and I'm a third-year biochemistry student.
And I'm Holly Hinnon, and I'm a third-year animal science student. Today, we will be working through practice problem number 7 from chapter 3.1 in the General Chemistry Workbook. You should begin by working on the problem yourself to see if you can get the answer. Pause the video now until you've completed the problem. Then we'll go over it together. To start off, we're going to need to figure out what the chemical formula of the compound we're working with is. First, let's go over the prefixes used in naming chemical compounds. For 1, we have mono. For 2, we have di. For 3, we have tri. For 4, we have tetra. 5, we have penta. 6 is hexa. 7, we have hepta. 8 is octa. 9, we have nona. And 10, which is the highest we'll go, is deca. Now, let's look at the compound used in the problem. The problem gives us dichlorine heptoxide. From this, we see the prefix di, meaning 2, and hept, meaning 7. From the rest of the word, we see that we have 2 chlorine atoms. And then if we remember that when we name chemical compounds, we have to change the ending of the second element to IDE, we see that the other element used is oxygen. So we know that we have the chemical formula Cl2O7. Now that we've written the chemical formula for dichlorine heptoxide, let's calculate its molar mass.
So to calculate the molar mass of dichlorine heptoxide, we first need to look at the atomic mass of chlorine and oxygen, and then add these two to get our molar weight. So first, when we look at the periodic table, we find that chlorine has an atomic mass of 35.45 grams per mole. And as stated earlier, we know we have 2 of them. So we have to times this number by 2. And this will give us 70.9 grams per mole. For oxygen, it has an atomic mass of 16 grams per mole. And as stated before, we have 7 of them. So we have to times it by 7, which will give us 112 grams per mole. And when you add these two numbers together, we get that the molecular weight is equal to 182.9 grams per mole. Now that we have the molecular weight, we can do some dimensional analysis to figure out how many grams of dichlorine heptoxide we have. So the problem tells us that initially we have 9.64 times 10 to the 24th molecules of dichlorine heptoxide. Now to get this into moles, we have to use Avogadro's number, which is 6.022 times 10 to the 23rd molecules per mole. So to set this up, we would start by putting 9.64 times 10 to the 24th molecules, and then dividing by Avogadro's number. We can see that the molecules will cancel out and will give us moles, which when you do the math is 16.01 moles of dichlorine heptoxide. Now that we have the moles, we can then make that into grams using the molecular weight that we had calculated earlier. So to do this, we would take our 16.01 moles and then times by our molecular weight of 182.9 grams per mole, and this will give us 2,927.9 grams of dichlorine heptoxide. But we can't stop there because now that we're at the end of our problem, we have to deal with sig figs. So throughout the problem, the thing that has the lowest amount of sig figs was the amount of molecules we had, which was 9.64 times 10 to the 24th. Now for this, there are only 3 sig figs. So for our original number, 2,927.9, we can only report this to 3 sig figs, which would be these 3, meaning that the 7 has to round over, which would then give us the correct answer of 2,930 grams of dichlorine heptoxide.
We hope that this video has helped with your understanding of naming compounds, finding molecular mass, and using dimensional analysis. Thanks for watching!